right? So, very good morning. I welcome you all for today's EMF class. Is my voice audible? Right, thank you. So, we have been discussing Smith chart, right? In one of my last class, I have discussed what is Smith chart, the construction of Smith chart, the applications of Smith chart, right? So those things I have discussed, and in my last class, I have done some related problems, right? So one is open circuited transmission line, and another one is short circuited transmission line, right? We have calculated or determined input impedance using Smith chart. We have determined input impedance for both open circuited transmission line and short circuited transmission line. So in this session, let us try to do some more related problems. So let me take one important problem. A transmission line of length 0.4 lambda has a characteristic impedance of 100 ohm and is terminated in a load impedance of 200 plus J 180 ohms. Find a bit voltage standing wave ratio, reflection quotient, B, voltage standing wave ratio, C, input impedance, right? C, input impedance, and extension for this, D, the location of just a minute. The location of Vmax and V minima if the line is 0.6 lambda long, right? So this is the question we have, right? Very important. So which covers almost all, right? Almost all parameters it contains: reflection coefficient, VSWR, input impedance, the location of Vmax and V minima, right? So all. A transmission line of length 0.4 lambda right? A transmission line of length 0.4 lambda. A transmission line of length 0.4 lambda, and its characteristic impedance is 100 ohms. Load impedance is 200 plus j 180 ohm, right? So this is the given data, and we need to determine a reflection coefficient, capital gamma reflection coefficient, and b VSWR, right, small s, and c input impedance, and the location of Vmax and Vmin, right? Vmax and Vmin in the sense what earlier I have discussed while discussing voltage standing wave ratio, right? Maximum voltage and minimum voltage. So voltage standing wave ratio is equal to maximum voltage to the minimum voltage. It is the ratio between maximum voltage to the minimum voltage. So we need to determine maximum voltage and minimum voltage, right? So the same problem here, as I have discussed earlier, there are two methods to solve this problem, right? Method one is mathematical approach, right? Reflection coefficient. So what is reflection coefficient? Is equal to ZL minus Z naught by ZL plus Z naught. So ZL is given, Z naught is known. Substitute, simplify, you will get the answer. Next, B bit voltage standing wave ratio 1 plus capital gamma divided by 1 minus capital gamma, right? So this is the formula we have to determine voltage standing wave ratio, right? If I'm not wrong, this is the formula, right, to determine voltage standing wave ratio, right? And input impedance Zn is equal to Z naught ZL plus J Z naught tan beta L divided by Z naught plus J ZL tan beta L, right? So these are the formula, and debit Vmax and Vminimum that we have to calculate from Smith chart. So these are the formulas we have, right? So reflection coefficient, voltage standing wave ratio, and input impedance. So substituting the given values, simplify, you will get the answer. So here beta L. So beta L is equal to, beta is 2 pi by lambda into L, right? L is given. L is 0.4 lambda, right? So substitute all those values, all the given values, simplify, you'll get the answer. So this is method one, right? Method two, using Smith chart, right? Method two, using Smith chart, we can get, right? Method two, using Smith chart. So using Smith chart, in my previous class, I have done one or two problems there, right? And step one, step two, step three to determine or to find out the given parameter, right? So step one, so what is the step one here? As you know, the Smith chart is having it is a normalized chart, right? Smith chart is a normalized chart, right? So therefore, we need to convert, right? We need to convert the given load impedance into normalized load, right? So therefore, ZL is equal to, so how much? 200 plus J 180 ohms, right? And Z naught is equal to 100 ohms. So therefore, normalized load, right? Normalized load ZL, right? Z small l is equal to ZL by Z naught, right? ZL by Z naught, right? And this is equal to 200 plus J 180 divided by 100. So we will get 2 plus J 1.8 ohms. So this is the normalized load, right? So therefore, R is equal to 2 and X equal to 1.8, right? R is equal to 2, X equal to 1.8. So that is the first point, right? Coming to the second point, locate the point 2 comma 1.8 on the Smith chart, right? Locate the point 2 comma 1 point on the Smith chart, and say A, right? And say A. So locate the point 2 and 1.8. So 2 and 1.8 means what? R is equal to 2 circle, X equal to 1.8 curve, right? The intersecting point, right? We need to identify the intersecting point of R is equal to 2 circle and X equal to 1.8 curve, right? So now let us try to identify that point on the Smith chart, right? So R is equal to 2, right? So if you can see here, this is R is equal to 2, right? So is it visible? Okay, let me um, right? So now, right? So I think it is visible to you now, right? So R is equal to 2 circle. I'm sorry, R is equal to 2 circle. Yes. So this is R is equal to 2, right? R is equal to 2 circle. So therefore, this is R is equal to 2 circle. This one. So this is R is equal to 2 circle, right? And X equal to 1.8 curve. X equal to 1.8 curve. Where it is? Right. So this one, X equal to 1.8 curve is this. So this is X equal to 1.8 curve, right? Right. So X equal to 1.8 curve, this one. So X equal to 1.8. So this is X equal to 1.8 curve is this, right? So therefore, the intersecting point, right? The intersecting point of R is equal to 2, right? R is equal to 2 and the intersecting point of R is equal to 2 and X equal to 1.8 curve is this. So this is the intersecting point, right? So this one, right? So this is the intersecting point, right? So this is the intersecting point, right? So therefore, this point, let us say, let us indicate it as A, right? So this point is A, right? So where A is 2 comma 1.8, right? With where A is 2 comma 1.8. So that is point A, right? So that is the first step, second step, right? So therefore here locate second point, locate the point 2.1.2 comma 1.8 on the Smith chart and say A, right? So that we have done, right? So is it clear up to? Next step, draw a circle of radius equal to OA. Draw a circle of radius equal to OA, right? Draw a circle of radius equal to OA, right? So O, we know A. What is O? Let me indicate that. So O is this one. This is center point, right? Center point. So this is O, right? This is O. Center point is O. That means R is equal to one circle here. So this is O, right? So therefore, we need to draw a circle with a radius O, right? With a radius O. So let me first draw the radius O. This one, right? So this is radius OA, right? So this is the line radius OA, right? OA line, right? So draw a circle with the radius OA, right? So this is O and this is A. So we need to draw a circle with the radius OA, right? So here, anyhow, it is it's somewhat difficult to draw it, right? So let me try. Let me try to draw the circle. Let me try. Try to draw the circle here, right? So with the radius OA, I'm drawing a circle. It may not be perfect, right? So this is the circle I have drawn. Right? So I have drawn not a perfect circle, right? But if you have the devices, right, then you can draw even more perfectly, right? So as I'm drawing on the screen, so it is not possible to get a perfect circle, right? So just you have imagined that this is a circle, right? So circle of radius A, right? So that is the third point, right? So draw a circle. So try to understand, right? So draw a circle of radius equal to OA, right? Now extend the line OA to the inner circle of the periphery, right? Extend the line OA to the inner circle of the periphery, and indicate point B, right? Extend the line OA to the inner circle of the periphery and indicate point B, right? Like this. Here I am. Let us try to extend. Right? Let us try to extend. Let me take. Right. So. Right. So this is a OA line, right? And this should be extended. Just a minute. Right. So extend this line. Extend this line to the this one. Right. So inner circle of the periphery is this one. Right. And let us say this point is B. Right. This is A. This is A. Right. And this is O. Right. So OA, the line OA, right? The line OA is extended to the inner circle of the periphery, right? The inner circle of the periphery, right? So this is the third point, right? Right. So now draw a circle of radius equal to OA. Extend the line OA to the inner circle of the periphery and indicate point P. Now, reflection coefficient. Reflection coefficient capital gamma is equal to OA by OB, right? Reflection coefficient is OA by OB, right? So measure, right? Measure what is OA from here, from this point to this point, how much, and from this point to this point, how much, right? You just measure using scale, right? You can measure using scale, right? The distance, the length of the line, physically you measure the length of how many centimeters, right? How many centimeters using this scale you measure, right? OA, this line, this length, OA, right? And OB, measure physically, right? Okay, let me. This one is OA from here to here, right? Is OA, and OB is from here to here is OB, right? So therefore, OA by OB, whatever the value you will get, right? OA by OB, whatever the value you will get, right? So you note it down there, right? And you will get the answer, right? So the value which you will get is 0.591, right? So this much you'll get, right? 0.591 if you calculate, right? If you measure OA and the ratio OA and OB, you'll get 0.51, and that is the reflection coefficient, right? And you can also determine the angle of reflection coefficient, right? The angle of reflection coefficient, right? So this one, this is the angle of reflection coefficient from here to here, right? From here to here, this is the angle of reflection coefficient, right? Angle of reflection coefficient. So therefore, you will get angle of reflection coefficient. You will get to be how much you will get? 31 degrees. You will get, right? 31 degrees. You will get. So this is how we can determine reflection coefficient using Smith chart, right? Next, let us go ahead. Fourth step. Identify the point where capital gamma is equal to 0.591 circle meets the positive real axis, right? Identify the point where capital gamma is equal to 0.591 circle meets the positive real axis, right? The positive real axis, right? And that is nothing but voltage standing wave ratio, right? That is nothing but voltage standing wave ratio, right? So here, this circle is nothing but this one. So this circle, is nothing but this circle is nothing but capital gamma is equal to 0.591 circle, right? So whatever the circle we have drawn with the radius OA, that circle is nothing but 0.591 circle, right? That is 0.591 circle, right? And we need to identify the point where that circle meets the positive real axis, right? So this is the positive real axis. So let me indicate with this is the positive real axis, this one, right? So this is the positive real axis, right? So this one is the positive real axis. Is it clear? So this one, this part, right section, right? So this is the positive real axis, right? So now indicate the circle, the point where the circle meets the positive real axis. So this is the circle, and here, so this is the point, right? So this is the point where capital 0.591 circle meets the positive real axis, and so this is the point, and this point is nothing but voltage standing wave ratio, right? This point is nothing but voltage standing wave ratio. How much is this? How much is this? So this point is nothing but how much? 4, this here. So this is 3 and this is 4, right? 4. So therefore voltage standing wave ratio is 4. right? So yeah, identify the point where 0.591 circle meets the positive real axis, right? And that point is S, which is equal to 4, right? And which is equal to VSWR, right? VSWR, right? So VSWR is 4, right? VSWR is 4, right? Next up, fifth point. Let us try to right. Let us try to determine input impedance. Input impedance, right? So in previous problem also I have determined input impedance, right? So what is the procedure? Move point B. So what is the length of the transmission line is 0.4 lambda, right? Length of the transmission line is 0.4 lambda. This data was given, right? So therefore, move point B move point B towards generator a distance 0.4 lambda, right? Move point B towards generator a distance 0. Lambda and indicate point C, right? So move point B towards generator a distance 0.4 lambda, right? So what is point B? This one, right? So let me zoom in. So this is point B, right? So this is point B, right? So can you see this? So this is point B, right? So we have to move, right? We have to move point B. So this is point B, right? So this one is point B. So we have to move point B a distance 0.4 lambda, right? Because the length of the transmission line is 0.4, right? So therefore, we have to move a distance 0.44 lambda towards generator, right? Towards generator in the sense clockwise direction. So 0.4 lambda in the sense what? What is this? This is 0.21, right? This is 0.21, right? So therefore 0.21 plus 0.4, which is equal to 0.61 lambda, right? 0.61 lambda. So this one is 0.21 and we have to move a distance 0.4. Therefore the total distance 0.21 plus 0.4 is 0.61 lambda. So therefore identify that, right? Identify that along the periphery. So this is 0.4 and this is 0.22, right? And we need to identify 0.61, right? So where we will get 0.61, 0.61. So here so what is this? This is 0.49, right? This is 0.49 and this one is nothing but 0.5 lambda, right? 0 or 0.5 lambda. That's because 360 degrees, 0.5 lambda, right? We need to move how much? 0.61 lambda, right? So therefore, what is the difference here? The difference is 0.11 lambda. So therefore, we have to move one more 0.11 lambda, right? This one 0.11 lambda is this one here, right? So 0.11 lambda, right? So this is nothing but so this one, so this is nothing but a total distance of 0.61 lambda from point B, right? So this is nothing but a total distance of 0.61 lambda from point B, right? So this is the point, right? So this is what we have point 5, right? So in point 5, move point B towards generator a distance 0.4 lambda and indicate point C, right? Indicate point C. Right? So this is 0.1 and this point is point C, right? So always we need to indicate point on the inner circle of the periphery. So this is point C, right? So this is point C, and now draw a line, joining the center and point C. This intersects capital gamma is equal to 0.591 circle at point D, right? So this is the next step. So draw a line joining the center and point C. Let us do it. Draw a line, right, from the center, right? So I hope you are getting. So if it is difficult to track, you watch the video once again, right? Right. So draw a line from the center, right? From the center. So this is the center, and this is point C. This is point C. And this is the center. This is point C, right? So let me draw a line. Right? So this is the line, right? So connecting point C and the center, right? So this is the line I have drawn connecting point C center, and this line intersects the circle, right? This line intersects the circle at point D, right? This line intersects the circle at point D, right? So identify the corresponding R circle and X curve of point D, right? Identify the corresponding R circle, right, and X curve, right? So this is the corresponding R circle is this, right? So not this as per the calculation, and this is somewhat different, right? And x curve. So actually this circle, so this circle is not perfect, right? The circle which I have drawn is not perfect, is not as per measurements, right? Therefore, if you identify the corresponding circle and curve, you will get. I will give you those points. R is equal to 0.4 and x is equal to input impedance. So therefore, Zin is equal to 0.4 plus J 0.72 ohms, right? So this is the input impedance, right? Input impedance of the given transmission line, right? So this one. So this point is nothing but the input impedance, right? This point is nothing but input impedance. This point is nothing but VSWR, right? And if you calculate that, right? So if you calculate that, you will get this is the input. And one more thing is the input impedance which you have measured from the Smith chart is the normalized value. So if you want to get the absolute value, Zin, let us say capital input impedance is equal to Z0 into Zn, right? So 100, Z0 is 100, that is the given value, 0.4 plus J72 ohms. So you will get how much you will get, 40 plus J72 ohm, right? So this is the input impedance, right? Input impedance of the transmission line, right? So this is the fifth point, and this is the procedure how to determine the input impedance using Smith chart, right? Now calculating V max and V minimum, right? Let us say this is the sixth point, right? V max and V minimum, right? Let us try to find out V max and V minimum, right? So V max and V minimum, what is the question here? See, the location of V max and V minimum if the transmission line is 0.6 lambda long, right? If the transmission line is 0.6 lambda long, right? So therefore, if the transmission line is 0.6 lambda long, right? If the transmission line is 0.6 lambda long. Lambda means what? 720 degrees, right? Let me convert in terms of degrees, right? So that it becomes easy, right? So lambda is 720 degrees. Therefore, L is equal to 432 degrees, right? In terms of degrees, 0.6 multiplied with 720 degrees, you'll get 432 degrees, right? So this is 432 degrees, right? So that means what? Here 360 plus 72 degrees, right? Which is equal to 432 degrees, right? And now to identify V max and V minima, right? You just listen. So here, so this line, as we know that this is the center line, right? So this is the center line, right? And the right half is the right half, right? Right half is positive real axis, and which is also V maximum line, right? Which is also V maximum line, and the left half, this one, the left half, this line is V minimum, right? V minimum line, right? So therefore, from this point, right? So this point is A, right? This point is A. From point A, move. Let me write here. From point A, move 432 degrees towards generator and find number of intersecting points of Vmax and V minima lines, right? From point A, move 432 degrees towards generator and indicate number of intersecting points on Vmax and V minimum line, right? So from point A, right? From point A, so this is point A, right? So from point A, move 432 degrees, right? 432 degrees. From point A, move 432 degrees. So from here to here, how many degrees? From here to here, it is 31 degrees, right? Earlier we have calculated angle of reflection that we have calculated, right? So by traveling 31 degrees, one time we are getting one intersection here, right? One time we are getting one intersection. So therefore, V max 1, right? V max 1 is obtained at 31 degrees, right? Is obtained at 31 degrees. If you convert this, and if you convert this into lambda, this would be 0.055 lambda, right? So similarly, if you go on moving, so 31 degrees from here to here is 31 degrees, right? And move on like this, right? Move on like this, and up to this point, how many degrees? From here to here is 180 degrees, right? From here to here is 180 degrees and plus 31 degrees, right? Plus 31 degrees. So therefore, overall we have moved how many degrees we have traveled? 211 degrees we have traveled from point A up to here, right? From point A up to here, up to this point, right? Up to this point we have moved to that. And here, at this point we are getting, let us say, this point is D dash, right? So at D dash, again we are getting one intersecting point, right? We are getting one intersecting point, and that is V minimum 1, right? V minimum 1. So V minimum 1, we are getting at 211 degrees, right? We are getting 211 degrees, and which is equal to 0.55 lambda, right? And moving forward, right? From this point, moving forward like this, right? Moving forward like this, and again to point A, right? So from point A to point A, how many degrees? 360 degrees, right? From point A to point A. From point A to point A, right? From point A to point A, 360 degrees, right? And how many degrees we need to move? 432 degrees we need to move. and again moving, right? And again moving, and this is 31 degrees. From point A to this line is 31 degrees. So therefore, so 360 plus 31 will get 391 degrees, right? So if you move from point A, again 31 degrees more, right? Again 31 degrees more, again you will get one more intersecting point on Vmax line, right? One more intersecting point on Vmax line, and that intersecting point is Vmax 2, right? Vmax 2, and which is 391 degrees, right? At 391 degrees, you will get maximum 2, V maximum 2. This point is 0.305 lambda, right? So we have moved from point A, right? From point A, we have traveled 391 degrees, right? So we have to travel 432 degrees. So how many remaining? Here 9 plus 41 degrees remain, right? So therefore, let us move 41 more degrees, right? So 41 more degrees means somewhere here we'll get here, right? So at this point we won't get any intersecting point. So therefore, moving, right, moving from point A about 432 degrees, moving from point A about 432 degrees, we will get 2 V maxima and 1 V minima, right? So 2 V maximas at this one and this one, and V minimum at this point, right? V minimum at 0.305 lambda will get. So this is how we can determine maximum voltage points and minimum voltage points on the Smith chart, right? So as the time is running, I have explained very fast. So if you fail to get this thing, you can go and watch